In the last video, we developed the central idea of this entire chapter, which is the work energy theorem, that the net work done by forces, or the work by the net external force, leads to a change in the energy of motion. Now, we want to take this idea and break this work up into two parts. So we have a net work. This is work by all the forces. W1, W2, W3, W4. But those forces can have two parts. There can be work by conservative forces, which are independent of the path taken. So anyone can do the calculation if you tell them the starting point and the stopping point, because they don't have to know how you went about getting there. And then there's work by non-conservative forces. These are ones where the path makes all the difference. And so until the person gets the problem assigned to them and they actually know the path taken by the object, no one can do this work calculation. So these are left completely to the student. They have to be able to do those. Now, if you don't know that a force is conservative, you have to assume it's non-conservative and you have to do the calculation. But for the ones that are conservative, we have potential energy. And we can get various functions that will be useful to us, enable us to solve for their works. Now what we want to do is we want to take these net works, all of these works by all these different forces, and we want to group them into one of the two camps. They're either in this camp called the blue camp, on the blue team, or they could be on the red team if you want. Except instead of blue and red, they're in the conservative force camp, or they're in the non-conservative force camp. So if we break these guys up, maybe this one in work number 2 happened to be due to conservative, and these guys over here were non-conservative, then we're not going to write them all out. We're just going to say WC and maybe WNC. Most of the time I won't write out conservative or non-conservative like I did here in the notes because I'm kind of lazy. But when I write this, notice there's a sum. Even though it's not written, you have to add up all the conservative works, and you have to consider all the non-conservative forces doing work over in Wn sub c. So, simply breaking them into two parts, here's your work energy theorem. W net is broken into two groups of works, and it's equal to delta K. But we know that this one right here, the conservatives, by definition, is the negative of the change in potential energy. So we can plug that right in here. So we have minus delta U plus WNC is delta K. Now instead of leaving the delta U over here with the works, we're going to move it over to the other side where the energies are at. So then Wn sub c is delta K plus delta U. Oops, lost my delta. And we'll put it right here. This is sometimes called the conservation of energy. Energy is always conserved if you count up all the energy in the universe. What we're talking about here is an object like a ball. And the ball has kinetic, there's energy of motion, and energy of position. Bank accounts. Remember, those are our bank accounts here. There's our bank accounts. There's the U bank account, there's the K bank account, and the total effect of everything is to put energy into the K account. That's what W net does. The WUs put their money into this account, the work conservatives. The overall effect of W net is to put it in the K account. So what's happening? Well, there's also somebody who can be taking things out. The Wn sub c's. If you count all the work that went in here, and remember that this is minus the work by U, so these guys actually look like this. They're going the other way. I should have drawn them the other way because they're a minus delta U. So if delta U goes up, this is negative work. If you add this guy, here's this guy, here's the work coming out to this guy, and there can also be work being done by non-conservative forces, and the non-conservative forces are whatever's left after you take this from that. And what does it do? it changes the total amount of money in the bank account. If Wn sub c is positive, the total amount of money in the kinetic energy, potential energy bank account goes up. If Wn sub c is negative, then the total amount of energy in the K plus U system go down. That's often true in the case of friction, and the object eventually has no kinetic and no potential and it comes to a stop. But you could put a motor or something and pump energy in and make it swing higher and higher or go faster and faster. Wn sub c can be negative. It can also be positive. Now, this is a perfectly good and valid way to write it. It's based on distinguishing the energies based on the type, motion, and position. But sometimes it's more convenient to describe them in terms of time. When did they occur? Not what type were they. So if we do that, we can rewrite this equation, which is just basically the work energy theorem. And we'll put in our definitions. Delta K is the final motion energy, final kinetic, minus the initial. That's what change means. And the final potential minus the initial potential. And instead of grouping them by types of energy, we're going to group them by whether they occurred at the end, in the final, or they occurred initially. So all the finals are going to go together. So I'm going to put the K and the U together. And I'm going to put all the initials together. The K and the U. Now, this looks like some energy of motion and potential. Well, that's the total. We're going to call that E. The total mechanical energy. And this is the final mechanical energy. And this, because it has I's, is the initial mechanical energy. So Wn sub c causes a change in this total energy of K plus U, the total bank account. If we write that in terms of our deltas, we get the work by non-conservative forces is equal to the change in the mechanical energy. And this is sometimes called the conservation of energy equation. Again, it's really just the work energy equation written with a different perspective. We're not talking about motion. We're not talking about emphasis on potential. We're talking about what's the total amount of money in the bank account. So the work by non-conservative forces causes a change in the total mechanical energy. Now, where did it go? Well, it goes into kinetic and potential that we're not considering in the system a lot of times. You drop something like a block onto a table, smack. Originally it had potential, maybe m, g, and some height. Halfway down, it had some potential and it had some kinetic. Right before it hit the ground, it just had kinetic. And then sometime later, it has neither. It's just stationary. Where did the energy went? It was transferred by Wn sub c. It was transferred into the table. It was transferred into the air molecule making sound. That's still kinetic. There are atoms moving around, vibrating. They go to your ear and vibrate on you. The bottom line is the energy is conserved somewhere, but we're not adding up these bank accounts. We're not adding up the vibration of the atoms in here, which we call heat. And when you put your hand, if you bang on something a lot, take out a hammer and hit on something like a nail a bunch and then put your hand on it, you'll notice it's hot. We've lost that because we've swept it under the rug. So the Wn sub c is because we're sweeping things under the atomic rugs. Now, if we were to count up all the atoms, then there wouldn't be any Wn sub c's. We wouldn't have any rugs. On the other side, the downside is there wouldn't be any rugs. You'd have to count up all those atoms. That's a course called statistical mechanics. That's very powerful and able to do a lot of things. So let's look at this equation that we've written now a little bit more carefully. The difficulty in making the calculations has all been isolated on the left-hand side. It's calculating these work by these non-conservative forces which depend upon the path. If you can make those calculations, then you can use this technique. If those calculations turn out to be really hard to make because the dot product is changing, the length of the force is changing, the angle is changing, something like that, then this chapter may not be a useful chapter for you in solving the problem, and you're going to need to try some other technique. But all the difficulties in the calculation are on this left-hand side. Now, one way that this would be an easy calculation is if the left-hand side turned out to be 0. All right? Well, what does that mean? If this turns out to be 0, if that happened to be 0, then we say that the change in the mechanical energy is 0. That means the mechanical energy is a constant. Now, physicists don't say constant. They say a much more sophisticated term. They say it is conserved. A person who plays chess doesn't play with the knight, or I should say the horsey thing, or the castle. They play with terms like knight, rook. We place our rooks on open files. We don't say we kind of put them over on the kind of open thing, right? So in the same way, there's a terminology used by technical people, and the technical term conserved, when people says there's conservation, what they mean is you found something that's a constant. So if E is a constant, then we're going to be able to bypass some of the harder math and just use simple algebra. This, when you can do this, is said to be the conservation of mechanical energy. So if the total work by non-conservative forces is 0, that means Wn sub c is 0, then the total mechanical energy of the system is conserved, i.e. delta E, which is EF minus EI, is 0. And we rewrite that to say, hey, you can write the final energy of the system, and it has to equal the initial energy of the system. So we can draw before and after pictures of what the system's energy was before a thing started, and then later, in a later time, and compare the energies, and we know the total energy of the system has to stay the same. Now, this isn't always true. This is only true if this is true. Work non-conservative is 0. And that doesn't mean that there can't be non-conservative forces in the system. There can be. But if the total of all of them, the ones taking money out of the energy at bank accounts and the ones putting energy into the bank account, happen to balance, then it's as if there is none, and we can say the energy of the system is conserved. Now, there are two types of potential energy formulas that would be useful in calculating up these energies. So I tell you the following. The gravitational potential energy of an object of mass n at a height h above the Earth is given by the formula U is equal to mgy, where y is the height above the zero potential reference point. So you have some place on the Earth or anywhere else, and you call that y equals 0. Then if you know a ball is sitting up, say, some distance, y equal 3 meters, you simply take the mass of the ball, 9.8 meters per second squared, and 3 meters, and that calculates the potential energy of the ball right here. Now, there is something about this formula. It was developed by calculating work where they assumed that y points away from the Earth. So you don't have any more the choice of how you put your axis. Another one is the spring. Often you have spring problems. The spring from the unstretched position x equals 0, if you stretch it some distance x, then the potential energy is 1/2 times the spring constant times x squared. These two potential formulas will enable you to calculate the works done by the conservative forces. In other words, to calculate the change in potential energy. There are others that we'll experience later in the course, but for right now, these two will get everything we need to do to solve problems. All right, in the next video, I'll solve some problems for you.